Hey there, Calc 2 folks. I'm back with another lecture in our series of lectures over the infinite series, where I want to go over a topic that was presented in section 10.4 that involves approximating infinite series. As we had noted, there are very few cases for series where we can determine the exact value of that infinite series, and there's often times where that determining the exact value might require a rather heavy analysis of the sequence of partial sums in that series, or just the overall behavior of the series. So what we often find is sometimes an easier task is to go about approximating the value of the series, where what we are going to have here is an approximation that can be refined or become more precise, and can be somewhat controlled by us, the user. So, it's going to be an approximation technique that can be a very good way of kind of going about and figuring out what a series value might converge upon without too much effort, in a sense, folks. So, what we are going to look at here is approximating a convergent infinite series, and I will tell you, this technique is going to involve the sequence of partial sums, right? We are going to be using the sequence of partial sums to begin approximating the value of S, and I should be a little more specific. We're going to be using the nth term in the sequence of partial sums to begin approximating the value of S. In this approximation technique, the nth term in a sequence of partial sums is going to be part of the approximation of our value of S. As we add up further into the sequence, as we determine the nth value in the sequence of partial sums for larger and larger and larger values of n, right? We are going to, in a sense, be becoming closer and closer to the exact value of S, right? So that is one of the ways that we're going to kind of go about controlling our accuracy is by how far we go into the sequence of partial sums in an attempt to approximate this value of S. But like I said, it's only part of that approximation. The other part of this approximation technique is going to deal with analyzing what we're going to call the remainder, right? We're analyzing the remaining portion of S, right? What's still beyond that sum of the first n terms, right? We've only added up through the first n terms when we consider the value of S sub n. The remainder is considering what is the value for the sum beyond those first n terms, right? And there is a way of analyzing that involves the process of integration, right? So what we do start off with here is assuming that we are dealing with a convergent infinite series and that it has positive terms, folks. This is not an approximation technique that works for non-alternating series. We are going to see an approximation well, let me take that back. This is an approximation technique that does work for non-alternating series. This will not necessarily be the way that we want to go about approximating alternating series, however. We're going to introduce ourselves to alternating series in a lecture video or two from now. And there's going to be a way also to approximate those that I'll introduce at the time. But right now, this is just the case for these convergent infinite series with positive terms. And up to this point, those are been the series that have also been allowable in our tests, those 4 fundamental tests for convergence. All right? So let's assume we've been presented with a series, and through one of the 4 fundamental tests of convergence, we were able to determine that it converged. Right? Now, to go about approximating the value of that series, we would have the following technique. Right? To begin with, right, one of the things we would have to note, right, this does rely a little bit on an if statement. To begin with, if the terms of our infinite series can be expressed as an explicit function of f, right? Or careful there, an explicit function of our index value of k. And when f is thought of as a continuous function with respect to variables x and y for values of x greater than or equal to c, right? The value of the remainder, that remaining portion, right, that gives us the value of s when we consider using s sub n to approximate s, right, is given by the value of r sub n equal to s minus s sub n. When we think about the remainder's value, right, that remainder is, in a sense, the exact value of s minus the portion we have by adding up through the nth term, right? So when we think about the value of r sub n here, its relationship to s and s sub n is as follows. It's really the difference between s and s sub n. Where we can go a little further with that statement, as I had said, we can use integration to go about approximating this value of r sub n. This is all given by, or such that I should say, that this value of r sub n is stuck between these two integrations. This lower value, right, it's greater than or equal to this integration from n plus 1 to infinity for f of x dx, and it's smaller than or equal to this value given here by the integral from n to infinity for function f of x dx. Right? R sub n is stuck between these two improper integrals, right? Where all of this is very specific to what is our index n. What happens to be the value of n that we have used in our nth term of the sequence of partial sums. In a sense, we're using the nth term in the sequence of partial sums to begin approximating s, where we can choose what our value of n is. We might consider using the first 10 terms, or maybe the first 25 terms. Well, that's going to determine the value of n here in that sequence of partial sums. And if we choose to use the first 10 terms, then the value of our remainder would be thought of as r sub 10. It is going to be s minus s sub 10. And that value for the remainder, r sub 10, will be stuck between this integral, this improper integral that starts at 10 plus 1, which would be 11, and continue up to infinity for f of x dx, and would be less than or equal to this improper integral that starts at just n. Again, in this example, we're considering where n is equal to 10, so this would start at 10 and continue up to infinity. The function f of x in these integrations is this function f that is being formed from thinking of the terms of our sequence. A sub k is this explicit function of our index. We're simply expressing it in terms of x, variable x, to relate it to our understanding of functions. And again, these are improper integrals, so this is going to involve some application of limits in their calculation, and we had discussed those before the break at the end of chapter, I believe that was chapter 8, that we had looked at improper integrals. All right, so this is the beginning of the approximation. This does go a little further, because notice we've discussed s sub n, and we've discussed r sub n and this result. How do we use those two to actually approximate s now? Is we take note that if I bring this into view, right? Furthermore, since r sub n is equal to s minus s sub n, right? Since r sub n is equal to s minus s sub n, this value of r sub n in our inequality here can be replaced with s minus s sub n, all right, in value. And we go, okay, well, how is that useful? Well, now we can use a little bit of algebra to make a statement about this value of s. Using a little bit of algebra, I can actually remove the quantity minus s sub n from the inside of this inequality to the terms found on the outside by adding its value to all three parts. The two integrals on the outside, right? The two improper integrals here found on the outside of this inequality, and add it to the inside of this inequality to the value of s. When we add it to the inside here, it's going to turn s minus s sub n into just simply s, but then we're going to add s sub n to these outer two quantities, where you'll notice I'll bring that into note here, right? This does have an implication to it, right? This all implies then that this value of s, whose value we're trying to approximate, must be greater than this calculation here found on the left, known as its lower bound, that starts at s sub n added to this improper integral from n plus 1 to infinity for f of x dx, and is always smaller than or equal to, right, this calculation found on the upper bound for s, right, where we take the value s sub n and add it to this improper integral, the improper integral from n to infinity, right? This is going to be our approximation technique on the value of s, right? The way we're going to get to the value of s is we're going to use our values of s sub n, right, the sequence of partial sums up through the nth term, and this fact, right, that we know about the remainder using the first n terms to approximate the value of s, right? We're going to, in a sense, calculate this inequality for the value of s, all right? Let's do that with an well, first of all, let's look at a proof. Let's get the proof out of the way. Let's give this a bit of a visual to it. This should go with a little bit of proof here, folks. All right, because again, we're going, how are we connecting integration to infinite summations, right? I know there's some application there, certainly, but let's look at this specifically here, right? The following is the proof of this result, first of all, right? And it begins, right, as follows. It's a bit of a visual proof here, folks. It's a bit of a geometrical proof of this result, right? To begin, assuming that s here equal to the summation from k equals 1 to infinity of a sub k, right? Assuming s is equal to this, if a bar graph, if a bar graph is formed where the height of the kth bar corresponds to the value of a sub k, and the width of the kth bar corresponds to the value of 1, then the area within each bar is also going to correspond to the values of a sub k, right? To begin with, assuming that s is equal to this infinite summation here, if we were to consider a bar graph forming in the xy coordinate space where the height of this bar, let me see if I can make this a little bigger. Okay, there we go, a little nicer. We can see the actual axes now, all right? Where if we consider the height of this bar being the values of a sub k, right? And the width of this bar being 1 unit in length, and notice these bars are all 1 unit in length, right? Or we might say here in width, height being this measurement here, width being this measurement here for each of these bars, right? Then what is also going to be true as that the area within these bars, right, is going to be equivalent to the value of a sub k, right? If this bar is 1 unit in height and 1 unit in width, then that bar has an area of 1 square unit. Certainly, what you will notice is that the two axes are not within scale, so that does not look like a perfect square, but that is in its space here, certainly 1 square unit of space. Here, this bar has a height of 0.25 units and a width of 1 unit, so it must have a area of 0.25 square units, right? This bar has a height of 0.111, right? And if it has a width of 1, then its area is 0.111 units squared, and so forth. To begin with, an infinite series, right, can be thought of as a bar graph. We're letting the heights of the bars be represented by a sub k, and the widths of the bars all be 1 unit in length. We'll have the result that the area within each bar will also correspond to the value of a sub k. Now, this is how we're going to connect it to the value of integration, folks. Is we are going to be looking at approximating the area within these bars using an integral calculation, right? If we take this a little further, right, we can go on to say, let me go ahead and have to scroll up here. So the value of S, when we think about it, that infinite summation will correspond to the sum of the area in all the infinite bars of the bar graph. Right? The value of S is going to be the sum of every single infinite bar in this bar graph. And that is why I do have the ... back here at the end, as this bar graph is going on forever to the right. We've only considered the picture for the first 10 bars here. Right? And then furthermore, what we can note is that the value of S will be equal to what will be the sum of the area found in the first n bars with the sum of the area found in what would remain after the sum of the area in the first n bars. The summation known here as the remainders value. Right? In the following illustration, the value of S sub n is actually represented by the area the values found here in the blue bars. Right? We might say, and this graph does go up above here, we just don't have enough space to give a nice illustration of this. So these bars are up here extending way out of picture, but as we get closer to the value of n, the bars do have a height that decreases in the manner illustrated, where the actual height is highlighted by these green dots in the picture. Right? And each of those bars is considered to have this width of 1 unit. So if that's the height and this is the width, each of the bars' areas will correspond to the actual value of that term in the sequence that's being summed here. And these blue bars up to the value of n are all going to highlight the value of S sub n. They're all going to, in a sense, their total area will describe the value of S sub n. From n, then, up towards infinity, right? Actually, I should maybe zoom in on this picture a little bit. Let's make it a little bigger, right? From the value of n up to infinity, right, here, we have our values of R sub n forming, the value found in these red bars. Now, I did not show all the red bars. I only think I showed the first 10 here, but there would be an infinite number of red bars that would follow, right? So in total, the blue bars area added to the red bars area will give the total value for that infinite series. All right. Now, these blue bars area, we can calculate using the value of S sub n. We just add up the first n terms in our infinite series, and that will give us the area found in these blue bars. As for the red bars, we are not going to add up towards infinity. Instead, we're going to rely on integration. All right? If I scroll down here and we focus our attention on the red bars, right? As for R sub n, the value of R sub n, the area in the red bars, right, to the right of n, to the values found to the right of n here, right? Note letting a sub k equal f of k, if y equals f of x is continuous and positive for values of x greater than or equal to n, then those values of R sub n will will always be less than or equal to the integral from n to infinity for f of x dx, right? Where the integral from n to infinity for f of x dx is actually going to correspond to the area trapped between the curve y equals f of x and the x-axis over values of x greater than or equal to n. What we're illustrating is this following picture here, folks, right? Let's see here if I can blow this up a little bit so we can get this into view here, right? But again, I'll explain. We're going to try to approximate, right, the area found in all these infinite red bars, starting at the value of the nth plus 1 term, which falls right after the nth term, and continues up towards infinity. Right? The way we're going to approximate the area in all the red bars is we're actually going to use the function y equals f of x, right? That describes the explicit function of our kth terms in our sequence. It comes from that explicit function of the kth term in our infinite series, right? We're going to consider that to be continuous in its behavior in terms of x, and we're going to begin integrating it from n to infinity. We're going to consider the integral starting here at n and continuing off to infinity. That integral calculation will actually correspond to the area trapped between this curve, y equals f of x, and the x-axis. And the red bars themselves will be trapped within that area described by that integration. And if they're trapped within that area described by that integration, then they have to be smaller than that area described by that integration. Right? So that is the right-hand side being proved in that result for R sub n. When we think about approximating the area in these infinite number of red bars, well, we're just going to use the functional description of our series, f, right? And consider integrating starting at the value of n and continuing up to infinity. The area within the red bars is always going to be slightly smaller than that area given by the improper integration there. It is certainly going to be a convergent improper integration, though, right? That function f of x is going to be convergent in behavior if our series is convergent. All right, take note. Now, as for the left-hand side result and its proof in the integration, let's take quick note there. We see a similar result. All right. Also note, I should maybe say, also note, similarly, right, R sub n will always be bigger than or equal to the integral that starts at n plus 1 and continues off to infinity for f of x dx. Again, where this integral starting from n plus 1 to infinity for f of x dx, oh, and I got a little typo there. Let me go back here. Again, where the integral from n plus 1 to infinity for f of x dx corresponds to the net area trapped between the curve y equals f of x and the x-axis over values of x greater than or equal to n plus 1. Right? Note this illustration. If we blow up this illustration a little bit so we can see it a little bit more clearly here in the video, right? Here we again have all our red bars, right? We're trying to approximate the area in all these red bars. We just learned that they will be smaller than the improper integral for this function f that begins at the leftmost bound on these bars, which is the value of n, right? What we can now note is the area in all these red bars may be smaller than the integral of this function f starting at n, but they're always going to be bigger than the integral of this function f starting at n plus 1, right? If I begin this integral at n plus 1, this area found to the right is completely excluding this portion between n and n plus 1, which also completely excludes this first bar in that calculation of the remainder. So this improper integral that begins at n plus 1 and continues off, that gives us this entire area under the curve, is going to be just slightly smaller than what would be the total area found in all the red bars. Right? That's what this result is telling us. So if we put this result together with this result in our proof, we get the overall proof, right? Thus, from the illustrations above, this value of r sub n must be stuck between, right, these two improper integrals. A lot of students get these backwards. They think of n plus 1 being greater than n, so they put that on the right side. But remember, these are bounds on this improper integration, where n plus 1 is actually going to cause a region of space under f that is actually going to be smaller than the area found in these red bars. And starting at n is going to produce this area under this curve that's actually bigger than r sub n. All right? Now, let's put this in the example. Let's actually look at an example now that we have the proof out of the way. All right? Consider the following example, right, for approximating this convergent series. Now, we should recognize this convergent series. This is 1 over k cubed from k equals 1 to infinity, right? That is what we would know as what? That is a convergent p series, right? We're dealing with a power of p equal to 3, and we know for powers of p greater than 1, this p series is going to be convergent. So this is a convergent p series. And let's consider developing, right, an approximation for that convergent p series using the first 10 terms, well, I should be careful there, the 10th term in the sequence of partial sums. Let's add up through the first 10 terms of this infinite series and consider using them to approximate this series. All right? Let's consider a situation above that where we have 10 blue bars to begin approximating the value of s. All right? Well, in that case, we would first calculate the value of s sub n. Note, s sub n, or in this case s sub 10, would just be equal to the summation from k equals 1 to 10 for 1 over k cubed, which is just 1 over 1 cubed, which is 1, 1 over 2 cubed, which is 8, 1 over 3 cubed, which is 1/27th, and sorry, this is 1/8, 1/27th. 4 cubed is 64, so that's 1/64th. This is 1 over 1/25th, 1 over 2/16, and so forth, all the way up through the 10th term in the sequence, 1/1000th. Now, if I add up these first 10 terms, now I'm not going to get a pretty fraction, not a pretty rational value whatsoever. This does produce this result. You can, what is that? Millions. 19,164,113,947 divided by 16,003,008,000, right? It does not give us a pretty ratio whatsoever. And I actually used Mathematica to develop this calculation, right? I went onto that Wolfram programming lab and used it to develop this actual fractional result, where if we approximate that out to 6 decimal places, 7 significant digits here, we get 1.197532 in value, right? We get this approximation out to the nearest, 10th, 100,000, 10,000, 100,000 millionth in value, right? We can approximate, in a sense, this out to this value here, right? And I'm just really choosing that length for just the moment. But in our approximation technique to begin with, you do want to carry that out a few decimal places, right? Now, as for the value of r sub 10 itself, right? R sub 10 we know is equal to s minus s sub 10, right? As for r sub 10 equal to s minus s sub 10, we would note that the value of r sub 10 is stuck between these two improper integrals, right? Where these two improper integrals form, right, with the above understanding here, right? In our case, the n has been replaced with 10, so our lower bound is going to begin at n plus 1, which is 11, and continue up to infinity in its improper integral. And since n is 10, our upper bound on r sub n is going to start at an improper integral of 10 to infinity. As for function f of x in both of these integrations, that comes from a functional description of the kth terms in our infinite series, right? 1 over k cubed expressed in terms of x is just 1 over x cubed. And we're going to integrate that improper integral with respect to x. And we should expect a convergent result here, folks, because we are dealing with the case for a convergent p series, right? These are both integrations that involve the exact same integrand. So maybe we'll take note to begin with. The antiderivative of 1 over x cubed is negative 1/2 over x squared, right? So, right, if we think about the left-hand bound, the integral from 11 to infinity for 1 over x cubed dx is going to be actually the limit then. Keep in mind, this is how we handle an improper integral, as we apply the use of a limit in this manner, where we're considering the limit here as b heads to infinity for the integral from 11 to b for 1 over x cubed dx, which is really the limit of this antiderivative evaluated across these bounds. The limit as b heads to infinity for negative 1 over 2x squared from over the bounds from 11 to b. If I evaluate this antiderivative from 11 to b, it gives me this result, where if I now evaluate the limit of that as b heads to infinity, negative 1 over 2b squared is going to head to 0, and what we're going to be left with is just the second term in the argument of the limit, 1 over 2 times 11 squared. Well, 1 over 2 times 11 squared is 121, so times 2 is 242, and we're left with 1 over 242, or about 0.004132 in value. What remains after using this decimal 1.1973 or 7532 to approximate s is going to be a value that is bigger than 0.004132 in value, or bigger than 1/242nd. 1/242nd in value. Right? As for what it's smaller than, we consider a similar integral, but now for the case of 10 being our lower bound in the integration. The exact same antiderivative is used, right? Exact same setup is used, but now we evaluate across the bounds from 10 to b, which gives us this result in the interior, and we see a similar result here. The first term in this argument of the limit heads to 0, which leads us with simply the second term, 1 over 2 times 10 squared. Well, 10 squared is 100 times 2 is 200, and our result is 1/200th. So the remainder, using s sub 10 to approximate s, will always be smaller than what would be 0.005 in value. So if we put that together with s sub n, we will be able to develop an approximation for the value of s sub 10. All right? So to begin with, r sub 10 is stuck between these two values, 1/242nd and 1/200th. And since r sub 10 is equal to s minus s sub 10, we can actually say S minus S sub 10 is stuck between these two values, right? And if S minus S sub 10 is stuck between those two values, that does have some implications about the value of S. Adding S sub 10 to all three sides of this inequality, the two outsides and the inside, will produce this result here. S must then be stuck between this result, bigger than S sub 10 plus 1 242nd, and smaller than or equal to S sub 10 plus 1 200th. And if we substitute in for S sub 10, that extremely cumbersome rational value, right, given by the sum of the first 10 terms, this quantity here, we substitute that in for S sub 10 on both sides of this inequality, and calculate one last time these summations here, right? We can then approximate S to the nearest, 10 to the negative fourth degree, which would be to the nearest 10th, 100,000th, 10,000th degree, to be somewhere between 1.2017 and 1.2025 in value. All right? We have this out to the nearest 10th, 100th, 1,000th. We're off by we have a range of about 0.0008, about 8/10,000th in value. We're accurate out actually to the nearest 100th in value with this approximation. We certainly could make this approximation more precise by increasing, going back here and increasing, right, what term in the sequence of partial sums we add up through. Instead of adding up to the first 10, we might consider adding up to the first 11. All right? If I do that, that will certainly make my approximation more precise. Or maybe we add up through the first 100 terms. Certainly we have computers nowadays that can handle this calculation up through the first 100 terms. All right? That would certainly give us a rather precise approximation, right? Out to a very high degree in terms of decimals. So, folks, this is an approximation technique that we have for approximating the nth term. Oh, careful there. Approximating the exact value of S in an infinite series. As we had noted, sometimes it's awful tricky to figure out the exact value of S. Where, as we can see here through a couple of quick improper integral calculations involving the exact same integrand, right, we can come up with an approximation that is accurate out to several decimal places and can be made more accurate, right, with just a little more effort involved. So, folks, that is the last video in this section of videos where we're looking at 10.4 and 10.5 material. This actually fell in 10.4, right, where we looked at some approximation technique. That this idea was brought up in 10.4. What you can expect to see now are some videos following. We have to look at 10.6, as I think I've hinted to that, where we spend some time looking at alternating series. And I will tell you some things are going to get a little easier, but there's going to be a little extra that we're going to have to talk about. And then that little extra is going to bring up what we call two more tests, two more complex, what we might consider a little bit more complex tests for convergence and divergence. And those are going to be the tests, the ratio and the root test. So that is section 10.7 material, folks. 10.8 just looks at putting it all together, folks. And we've been doing that along the way, so we're not going to spend a ton of time in section 10.8. But it is also a practice section out there. Certainly, it's good practice if you're looking for something to really test yourself. So, folks, I hope you're doing well. I hope you're hanging in there. I know I am. I've enjoyed the few sessions where I've been able to meet with folks on Collaborate. That certainly helps to take my mind off things. And if you are looking to get your mind off things, I hope you jump in a Collaborate session and spend some time with us. Other than that, I'll see you in the next video.